Hey everyone, and welcome back to AI Paper Podcasts, where we do deep dives on the latest research in AI.
And sometimes not so latest research.
Well, yeah, true. Sometimes we go back a little bit, but today we're diving into a fascinating paper all about making large language models faster and more efficient.
The big LLMs.
The big LLMs, exactly, by Ramon Calvo Gonzalez and his team.
And they're taking on a huge challenge, probably the one we're all thinking about.
Yeah, compute costs.
Compute costs. Those things are expensive. Millions of dollars per month. For high traffic applications, imagine shaving that down.
And that's what they're looking at. And they're doing it without sacrificing accuracy.
That's the key, right?
Yeah.
You don't want to lose all the performance.
Right. And the idea is kind of counterintuitive. They're saying that the layers in these LLMs might be more independent than we think.
Right. Traditionally, we think about LLMs and how they build these hierarchical representations, where each layer builds on the previous one.
Yeah.
But this paper is challenging that assumption.
So are you saying we've been wrong about these models?
In a way, yeah.
Okay.
They found that even when you shuffle or prune layers,
Really?
the performance doesn't completely tank like we would expect.
Wow, that's crazy.
So the paper introduces this idea of effective depth.
Effective depth.
Which is basically the shortest path you need to leverage all the model's latent representations without, significantly compromising performance.
So, okay, that's make more sense to me now.
It's like finding shortcuts within the model architecture.
Oh, interesting.
Yeah.
Okay, so, but how does this actually make these massive LLMs run faster?
Well, this is where the core innovation comes in. Parallelization.
Okay.
So they're using this newfound layer independence to run pairs of consecutive layers in parallel.
So two separate processing streams happening at the same time.
Yeah.
Like two cooks in the kitchen.
Exactly.
Instead of just one.
And they actually tested this approach on real LLMs, not just in theory.
Oh, wow.
And they achieved a 1.2x speed boost on Llama 2, which is quite remarkable.
That is a significant improvement.
Yeah.
So I'm guessing to make this actually work in practice, they had some hurdles they had to overcome.
Oh, yeah. There were challenges.
Technical challenges.
Absolutely. Yeah. So naive parallelization wouldn't work because of something we're all familiar with, GPU saturation.
Right.
So if you try to cram even more computation onto already maxed out GPUs, well, it's just going to create a bottleneck.
That makes sense.
Yeah.
So how did they get around that?
Their solution was to combine layer parallelism with the existing tensor parallelism from Megatron.
Okay.
So it's a bit of a carefully choreographed dance.
Right, because we're splitting the model across multiple GPUs.
Yeah.
But we're also taking into account this parallel processing of the layer pairs.
It's a delicate balance, yeah.
That sounds incredibly complex.
It is. And there were specific challenges they had to address. For example, layer normalization layers are very sensitive to the distribution of their input.
Right.
And this gets disrupted when you change the order of operation.
Of course, yeah.
So they had to find ways to make sure everything stayed accurate, despite this modified computational graph.
So we have layer independence leads to this parallelization.
Right.
But it's not just a free-for-all.
No.
We have to worry about the GPU limitations, handle normalization carefully, make sure the results are still valid.
Right. It's a bit of a balancing act.
It is.
Speaking of results, you want to hear about those speed gains?
Yeah. Let's get into the nitty-gritty.
All right. So buckle up. They achieved up to 1.29x improvement on single token generation for long sequences in Llama 2.
Okay.
That's almost a 30% boost.
That's pretty impressive.
Oh.
But I imagine there is a trade-off. You don't get something for nothing.
You're right. While the performance degradation was relatively small, it was still there, and it seemed to get a little worse as models got larger.
Oh, so bigger models, bigger headaches.
Yeah. It seems like the bigger models, they have tighter coupling between layers.
So they're less amenable to this parallelization.
Right. But they did mention that fine-tuning could help.
Oh, yeah.
So they found that targeted fine-tuning after applying layer parallelism can partially recover the lost accuracy.
So it's like giving the model a little bit of extra training to adjust.
Yeah, exactly.
So a trade-off, but you can possibly mitigate the drawbacks.
Right.
That's promising.
Yeah. But what's really fascinating is that this paper also highlights some limitations that open up new questions. For example, they found that smaller models don't see much benefit.
That makes sense, because if the layers are already deeply intertwined, there's less room for this parallel processing.
Right.
Seems like this technique is really tailored for those massive cutting-edge LLMs
Yeah.
that are pushing the boundaries.
And even with those large models, achieving the full baseline performance, even with the fine-tuning, remains a challenge.
Oh,
And maybe, most intriguingly, figuring out the optimal layer grouping strategy, what they call the true effective depth, is still an open question.
so there's still a lot of room for exploration. Figuring out how to best apply this technique for different models and different tasks will be crucial.
Absolutely. It opens up a whole new area of research in LLM optimization.
But before we get ahead of ourselves, maybe it'll be helpful to dive into some specific details about their implementation and the results.
Yeah, let's get into the nuts and bolts.
Are you ready for part 2?
Let's do it. So, what's remarkable about this research, it goes beyond just, proposing parallelization. They actually really dug deep into understanding this concept of effective depth.
Okay.
They systematically tested how different transformations to the model's layers, impacted performance.
So they didn't just start randomly parallelizing things. They wanted to actually prove that these layers were independent.
Exactly, yeah.
So they experimented with shuffling, merging, and even pruning layers.
Yeah, and they used those heat maps we talked about
Right, yeah.
to visualize the impact of each transformation.
Those were really helpful too for seeing what the trade-offs were.
Yeah, absolutely.
Where can you make changes without causing a huge drop in performance?
Right, exactly.
So let's start with shuffling. What did they find when they rearranged layers in the middle of the model? Did that totally mess things up?
Surprisingly, no. So shuffling layers in the middle of the model didn't drastically change the perplexity.
And for our listeners who aren't familiar with perplexity,
Yeah.
how would you quickly explain that?
Yeah. It's basically a measure of how well the model predicts the next word in a sequence. So a lower perplexity means the model is more confident in its predictions.
Got it.
And what they observed was that even with shuffled layers, the perplexity remained relatively stable.
Interesting.
So this suggests that those middle layers, they might be operating on a similar level of abstraction,
Okay.
and that their precise order, it's not as crucial as we might have assumed.
So it's kind of like rearranging the furniture in a room. You're changing the look, but the room still functions.
Yeah, it's a good analogy.
Okay, so what about merging layers? Is that like combining two rooms into one bigger room?
It is. It's a good analogy. But here's the interesting part. Merging layers didn't really provide a significant advantage over simply pruning them.
Yeah.
So it suggests that averaging the weights of two layers doesn't necessarily create this super layer that captures the best of both worlds.
So sometimes less is more.
Yeah, exactly.
You want to streamline the model, you got to get rid of a layer altogether.
Yeah.
Okay, what about pruning? Was that as detrimental to performance as you would think?
Pruning did lead to a larger increase in perplexity compared to parallelization,
Right.
but pruning actually reduces the model's size,
Yeah.
which is a huge win for memory efficiency.
Right, yeah. So a smaller model means less memory and potentially even faster inference.
Exactly.
Okay, so that's a trade-off worth considering. But ultimately, these researchers were most interested in this parallelization approach, right?
Yes, and they went beyond just simple parallelization. We already talked about how naive parallelization can lead to GPU saturation.
Right.
So to avoid that, they had to get a little bit creative with the computational graph and leverage tensor parallelism.
Okay, so let's break this down for our viewers. We know that tensor parallelism involves splitting the model's parameters across multiple GPUs. So how did they combine that with their layer parallelism idea?
So they essentially took those parallelized pairs of layers and distributed their weights across multiple GPUs.
Okay.
So instead of two layers working sequentially on one GPU, each layer in the pair gets its own dedicated, GPU horsepower.
That's clever. So they're not just parallelizing the layers themselves, they're also parallelizing the way those layers are processed.
Exactly.
It's like a double dose of efficiency.
Yeah, exactly. And this approach led to those really impressive speed improvements, especially for those long sequences that, really challenge LLMs.
Yeah.
But I think it's important to highlight some limitations.
Right, because no approach is perfect, and this one is no exception. There are always trade-offs. What were some of the challenges that they ran into?
Well, one thing they pointed out is that smaller models don't see as much benefit from this technique. It seems like those smaller models have tighter coupling between layers, so there's less room for effective parallelization.
So this is really a technique best suited for those massive cutting-edge LLMs.
Yeah.
The ones that are already pushing the limits of compute.
Yeah.
Makes sense that those would benefit the most
Exactly.
from an efficiency boost.
Yeah. And even with those large models, there's still the issue of not fully recovering the baseline performance, even with fine-tuning. There seems to be a ceiling to how much accuracy you can regain after making these structural changes.
So there's a bit of a compromise there.
Yeah.
You gain speed, but you might lose a tiny bit of accuracy.
Yeah.
And perhaps the biggest unanswered question they raise is, how do you determine the optimal layer grouping strategy?
Yeah, they refer to this as finding the true effective depth, and there's really no foolproof way to figure that out right now.
So more research is needed.
Yeah.
Which is exciting.
Yeah, it's exciting.
This paper opens up a whole new area of exploration in LLM optimization. It challenges our assumptions about how these models work, and it presents a promising path towards making them faster and more efficient.
Absolutely.
And faster, more efficient LLMs could revolutionize all sorts of applications.
Yeah.
From chatbots to machine translation to content creation.
Yeah, exactly.
The possibilities are endless.
Absolutely, yeah.
But I think our viewers would really appreciate some concrete examples of their implementation.
Yes, absolutely.
And the results.
Yeah.
So how about we move on to part 3?
Yeah.
And we can delve into those details.
Let's do it.
All right, let's get specific. We've talked theory, we've talked challenges, but how do they actually put this layer parallelism into practice?
Yeah.
I think our viewers are really eager to hear about the nitty-gritty.
So they actually built this thing and ran it on real hardware.
Okay.
It wasn't some wimpy setup either.
Spill the beans. What kind of computational muscle are we talking about?
So they used a node with 2 NVIDIA A100 SXM4 80 GB GPUs,
Okay.
4 AMD EPYC 7742 CPUs, and a massive 512 gigabit of RAM.
Ooh.
Yeah, that's some serious firepower.
That tells you something about the scale of these LLMs.
Yeah.
They're not messing around with toy models here. So what specific LLMs did they use for testing?
They focused on 2 models from the Llama family, Llama 2.7b and Llama 2 3.23b.
Okay.
So pretty representative of the state of the art.
Yeah, large, powerful models.
Yeah.
So they're testing layer parallelism with these 2 GPUs, splitting the work between them. But how did they actually measure the impact? What were they looking at?
They focused on 3 key metrics: inference speed, in-context learning performance, and the potential to recover accuracy through fine-tuning.
Okay.
So let's start with inference speed, because that's really the heart of this research.
Yeah. We want to know, how much faster can these LLMs generate text with this new technique? So what were the results? Did they actually see a speed boost?
They ran a whole bunch of tests, varying sequence lengths and, different configurations of layer parallelism. And the results were actually pretty impressive.
Oh.
So for Llama 2.7b, they saw an average speedup of 1.29x on single token generation with long sequences. When they parallelized up to 14 layers.
That's almost 30% faster. That's a substantial improvement.
Yeah.
What about Llama 2 3.23b? Did they see similar gains?
Yeah. For that model, they achieved a speedup of 1.22x when parallelizing up to 10 layers.
Wow. So consistently good results across these different models.
Yeah. And they even pushed it further, parallelizing even more layers to see where those limits were.
I bet there's a trade-off there. So faster speed, but maybe at the cost of accuracy.
Yeah, you're absolutely right. They did observe a drop in context learning performance when they parallelize too aggressively. So it seems like there's a sweet spot.
Makes sense.
You can't just keep splitting things up without some consequences.
Right. You could just keep cutting corners without some impact.
Yeah.
But what about fine-tuning? Could they recover some of that lost accuracy by fine-tuning the model after applying layer parallelism?
Yeah, that's a great question. And that's exactly what they investigated next.
Okay.
So they took Llama 2 3.23b, applied layer parallelism to a specific set of layers, and then fine-tuned just those layers on a subset of the training data.
So not the whole model.
No, just the parts that were affected by the parallelization.
Okay, so it was like a very targeted intervention. Did it work? Were they able to regain some of that accuracy?
It did. They saw a significant recovery in performance, particularly on the MMLU benchmark, which measures multitask language understanding.
Okay.
So after fine-tuning, the model achieved 94.4% of the baseline performance.
So almost back to full accuracy.
Yeah.
But still with the benefit of that faster inference.
Yeah, exactly, yeah.
That's a pretty compelling result.
Yeah.
But they did mention some limitations, right? No approach is perfect.
Yeah, of course. So one limitation is that smaller models don't benefit as much from this technique. Their layers are more tightly coupled.
Right.
So there's just less opportunity for parallelization to really make a difference.
Right. So this really is a technique that shines with those massive state-of-the-art LLMs.
Yeah.
The ones that are really already pushing the limits of what's computationally feasible.
Right, exactly.
And even then, there's still this challenge of finding the optimal layer grouping strategy,
Yeah,
what they call the true effective depth.
which remains an open question, yeah.
So more research is needed
Absolutely.
to figure out how to best apply this for different models and different tasks.
Well, this has been a fascinating taper. It's challenged some of our assumptions about how LLMs work, and it's presented a really promising avenue for making these models faster and more efficient,
I agree, yeah.
which could revolutionize all sorts of applications.
Absolutely.
From chatbots to machine translation to content creation. I mean, the possibilities are endless.
Yeah, absolutely. And this research is a significant step towards making those applications more accessible, more scalable.
Right.
It's an exciting time to be working in this field.
It is, yeah.
Well, on that note, I think we've reached the bottom of this deep dive.
Yeah.
Thank you so much for joining us, and we'll see you next time for another AI Paper podcast.
Until then.